Now we come to the second part of this question. So in this linear ionic crystal, line of two capital N ions of alternating charge plus or minus Q with a repulsive potential energy A divided by R to the power N between nearest neighbors, we showed that at equilibrium separation we have this expression for the potential energy. Now in part B, let the crystal be compressed so that the equilibrium separation R0 goes to R0 times 1 minus delta. Show that the work done in compressing a unit length of the crystal has the leading term 1 over 2 C delta square, where C is n minus 1 Q squared times natural logarithm 2 divided by R0 square. And note that we should not expect to obtain this result from the expression for u of r0, but we must use the complete expression for u of r. Okay, now in this part of the problem, we are compressing this crystal. There is an external force being used to compress the crystal, and the equilibrium separation decreases from r0 to r0 minus delta r0. The work done by this force, so in part B of this problem, the work done by the external force is equal to the change in potential energy according to work potential energy theorem. Remember that work done by the internal force is minus the change in potential energy, but by the external force is plus the change in potential energy. Now, what will be the change in potential energy? It will be the potential energy evaluated at R0 minus delta R0, the new potential energy, minus the initial potential energy, U of R0. So this is going to be equal to final potential energy minus the initial potential energy. Now, R0 is going to be R0 times 1 minus delta, where delta is much less than 1. It's a small compression. So if I look at U of R in the vicinity of R equals R0, I will find, or in other words, delta is much less than 1. I will find the following approximation using Taylor series expansion. It's the potential energy evaluated at R0 plus the derivative of potential energy del U del R evaluated at R0 multiplied with R minus R0, and we have 1 over 2 factorial second derivative of potential del square U del R square evaluated at R equals R0, R minus R0 square, and then there will be higher order terms. So we can see that the first term, the first derivative term here is going to be equal to 0. Why? Because this is at equilibrium. Equilibrium, first derivative of the potential with respect to R has to be 0. The force is 0. So we find that the potential is U evaluated at R0 plus 1 over 2 factorial second derivative of U del square U del R square evaluated at R is equal to R0, R minus R0 parentheses squared and higher order terms, and R minus R0 is going to become R minus R0 plus delta R0. Okay, so we see that this difference between u of r0 minus delta r0 and u of r0 is 1 over 2 factorial. So if I subtract from this u of r0, I will find that this is basically evaluated at this value. I will find that the difference is this term. So basically we find delta u is equal to 1 over 2 factorial second derivative of u with respect to r evaluated at r0 multiplied by r minus r0 squared, which is evaluated at r is equal to r0 minus r0 times delta. So this is going to give me 1 over 2 factorial second derivative of the potential del square u del r square evaluated at r0. Now r is r0 minus r0 delta. Subtracted from this r0, I obtain r0 delta. So r minus r0 is r0 delta. So this is r0 square delta square, which is equal to 1 over 2 c delta square. So the potential energy is in this form. So remember that we're supposed to show the leading term 1 over c delta square is in this form, and c is equal to this expression. Okay, so we have found c. If we write it this way, 1 over 2c delta square, if we write it this way, the delta squares will cancel here, and we will find that c is equal to 1 over 2 second derivative of the potential del square u del r square evaluated at the equilibrium separation r0 multiplied with r0 square. So that's basically how we're going to find the expression for c. Now we have the potential u of r, which is capital N times the repulsive term a divided by r to the power n minus alpha q square divided by r, where alpha is equal to 2 log 2. That's what we found in part A. So if I take the first derivative, del u del r, I obtain del r of n times a r to the minus n minus alpha q square r to minus 1. This is something I have done before, and this gives me capital N times minus n a r to minus n minus 1 and plus alpha q square r to the power minus 2. Now I need the second derivative, del square u del r square evaluated at r is equal to r0, the equilibrium separation. This will be capital N times minus n minus 1, capital A, r to the power minus n minus 2. Then I have minus 2 alpha q square r to the power minus 3. And this is going to be evaluated at r is equal to r0. That's what we need for C. this evaluated at r is equal to r0. And that gives us capital N times n plus 1 a. You can see that this minus sign is going to become a plus here. Divided by r0 to the power n plus 2 minus 2 alpha q square, 2 alpha q square divided by r0 to the power 3. All right. Now I note that I'm looking for an answer for a unit length of the crystal. What is the total length of the crystal? Total length of the crystal is equal to the number of ions, which is 2n, and we have a separation r0 between the ions. So it's going to be equal to 2n times r0. So the number of ions 2n multiplied by r0 is equal to 1. So that's for the unit length of the crystal. So 2 capital N r0, it's actually for 2 ions, for example, the crystal length is 1 r0. It's 2 capital N minus 1 times r0. But for a large number of ions, this is going to be approximately equal to 2 capital N r0. So that 1 is not important. So this is equal to 1. So we note that we have to use this. That is a unit length of the crystal. And that means N is approximately 1 over 2 r0. Because total crystal length is approximately 2n r0. So it's 1 over 2 r0. Okay, for capital M. Now I go to the second derivative that I have found, del square u del r square, evaluated at the equilibrium separation r0 is equal to, now I'm going to substitute for capital N 1 over 2 r0. So this will be 1 over 2 r0. Then I have n plus 1 a r0 to the power n plus 2 minus 2 alpha q squared divided by r0 cube. Now from part A, I know that r0 to the power n is equal to na r0 divided by alpha q square. This is part A at equilibrium. We have found this relationship for r0 to the power n. So we can use that, and this gives us basically n times a is equal to alpha q square r0 to the power n divided by r0, r0 to the power n minus 1. So this is equal to 1 over 2 r0. For n times a, I substitute alpha q square r0 to the power n minus 1. Then I have n plus 1 and r0 to the power minus n minus 2. And then I have minus 2 alpha q square r0 to the power minus 3. And this is equal to 1 over 2 r0. So n minus 1 with minus n minus 2 is going to give me a minus 3. So this will become alpha q square n plus 1 divided by r0 to the power 3 minus 2 alpha q square divided by r0 to the power 3, r0 cube. And that is equal to, now I have alpha q square parenthesis here, n plus 1 minus 2. So I can write this as 1 over 2r0 in alpha q square over r0 cube parentheses n plus 1 minus 2. So I reach the following answer. So this is equal to alpha q square divided by 2r0 to the fourth power n minus 1. Okay. Now, what is 1 over 2 factorial? Del square u del r square evaluated at r0, r minus r0 square. R is r0 times 1 minus delta. So r minus r0 is once again delta times r0. This is equal to 1 over 2 del square u del r square evaluated at r0, r0 square delta square as we have found, which is equal to 1 over 2 c delta square. So we obtain c is equal to the second derivative of u with respect to r multiplied by r0 square delta square. Now, what is the second derivative evaluated at r0? It is alpha, where alpha is 2 log 2 q square n minus 1 divided by 2 r0 to the fourth power. You see these delta squares cancel here, 1/2 cancel. r0 to the fourth power, but I have an r0 square here, so this becomes r0 square. 2's will cancel, and that gives me my final answer for c. C must be equal to q square n minus 1 natural logarithm 2 divided by r0 square. That's the value of c. So let's see if that's the suggested answer. The suggested answer for c was n minus 1 q square log 2 divided by r0 square. Once again, this result is a CGS result. For SI, q square will be replaced with 1 over 4 pi epsilon 0 q square. All right, so in this second part of the problem, we have applied an external force to compress the crystal. The crystal equilibrium separation was R0. The new separation is R0 minus delta R0. And when we do that, we can use the work potential energy theorem. The external force, work done by the external force, is the change in the potential energy. So the potential energy goes from U of R0 to U of R0 minus delta R0. If I look at the potential energy in the vicinity of R0, it is u of r0 plus the first derivative evaluated at r0, which is 0 because it's an equilibrium condition, plus 1 over 2 factorial second derivative evaluated at r0, r minus r0 squared. New r value is r0 minus delta r0, so this becomes delta square r0 square. And this subtracted from u of r0 basically gets rid of this term, and we obtain to first order the second derivative 1 over 2 factorial del square u del r square, del square u del r square, evaluated at r0 multiplied with r minus r0 square. This is set equal to 1 over 2 c delta squares cancel, and also 1 over 2's cancel here, and we obtain c is equal to second derivative of u with respect to r evaluated r0 multiplied with r0 square. Okay, so this is our u of r. Alpha is 2 log 2 from part A. We already had the first derivative in part A. We take another derivative, and then we substitute for 2n r0, 1. The total length of the crystal is actually 2n minus 1 times r0, but 2n can be a large number, so this is approximately 2n r0. So n is 1 over 2 r0, and if we substitute for n 1 over 2 r0, and for r0 to the power n and a r0 over alpha q squared, the answer we had from part A, we obtain alpha q squared over 2 r0 to the fourth power n minus 1. So if we substitute for alpha 2 log 2, we obtain our final answer for C in CGS units, and in SI we have to replace q squared with 1 over 4 pi epsilon 0 q squared.